Way to go.
Hey. So thank you very much for attending and giving me the chance to talk about the work of really quite a few people at Berkeley and at other institutes. I have a cold and a bit of a hoarse voice, so have to deal with that. I don't feel bad, but it might be painful to listen to. So scalable genomics in the cloud with Atom and big data genomics. So big data means different things to different people, but I think that particularly whole genome sequencing genomics clearly satisfies anybody's definition of big data. It has volume. Large genome centers have now data centers from tens to hundreds of petabytes in scale. A given research study might be in the realm of 100 terabytes, and as we transition to large, healthcare applications of genomics, will quickly be in the tens and hundreds of petabytes, at least in sort of broad data sequencing. It has velocity. A health study or a longitudinal research study will produce hundreds or thousands of samples per month, which means hundreds of terabytes coming in a month. The data doesn't just go into a data lake where you read it later. You need to process the data, add it, merge it, reanalyze, because each new sample gives you new insights to previous samples you've seen. So it's a continuous influx of data that needs to be reanalyzed. There's also a response time need. So for clinical applications, pathogen surveillance, biodefense decisions, we can't deal with days or weeks response times. We need to be able to elastically scale very quickly so we can do the processing that needs to be done within a matter of hours. And there's a variety of data. So I work largely in sequencing DNA genomics, but there are many assays that are read out through sequencing, and so there's a wide variety of functional genomics, DNA sequencing that apply. So two other aspects that I think are particularly relevant to research and clinical applications is portability. That workflows need to be portable, and I work for several large genome centers, and they have very elegant, bespoke custom solutions to their data architectures. It works okay at the scale they're currently at, but it's completely non-portable to other places, and a lot of wasted effort there. So if we could leverage some of the standards in big data technologies which are emerging, we could have a reusable solution. And finally, when portability doesn't exist, reproducibility doesn't exist. You can't you can't take a FDA-approved test. You can't take a scientific paper that you read and reproduce it because you don't have the infrastructure. It's not portable from place to place. So talk a little bit more concretely. Your standard genome sequencing DNA pipeline looks something like this. You do sequencing, produce FASTQ files. You run a step that does alignment to a reference genome. You have a QC and a normalization step. You actually detect variant positions. You call genotypes in individual samples and as a collective population level. Once you produce those genotypes, if you have an ongoing study, you need to have a cumulative data warehouse to put those into, so you can analyze them over time, and then that's just the infrastructure to actually then do the kind of sort of data science that you want to do in bioinformatics. So we want to associate genotype to phenotype, both for germline and then for true normal studies in cancer. And then there's a slew of downstream visualizations, machine learnings, integration with other data sources that needs to be done. So there are solutions for each of these that exist in current pipelines. Again, they often are bespoke and non-portable. For each of these steps, we have solutions which either exist or are underway that use the BDG architecture I talked about, but importantly, it's also modular. Like you don't need to you can put in your own third-party solution at any one of these steps as long as you conform to the interfaces. We're not just selling a turnkey solution. We want an ecosystem that you can mix and match as you like. And so that gets this evolutionary approach that we don't want the problem of yet another competing data standard. Either that would fail, or if we were successful and took maybe 30, 40, 50% of the mind share, that also would be a bad result because we would fragment the field, fragment the data standards, fragment the pipelines. What we really want is a re-implementation of standards. So the BAM, VCF type formats that came about in the 1,000 Genomes project, those worked. And what we can do is build on those in a way that uses big data standards to produce computable schemas that represent that data, You produce data formats which are more suitable for cloud compute, but without breaking compatibility with existing standards. And then the best way to invent a standard which is not used is to not have the tool chain that actually makes it useful. So I mean, the entire ecosystem of the BGG ecosystem is the tool chain that you'd use to use those formats. So one sec. So I use the terms Atom and BGG a bit interchangeably, so I'll make sure it's clear what it is. BGG, Big Data Genomics, is the umbrella project, of which Atom was one of the first major core projects. So I'll use Atom and BG a bit interchangeably. Atom BG, it's a set of data formats, APIs, programming language, libraries, and a command line interface for data processing and analysis of next generation sequencing on compute clusters. It takes a greenfield approach to implementation, but takes a interoperable approach with existing standards. So the project was designed from the ground up to use emerging standards in big data. So Apache Spark, Paschall I'll talk about, Avro to define schemas rather than to have the sort of bespoke accepted standard, so you can actually compute and generate code based on a schema. Deployment using Docker for reproducibility, and deployment on AWS and other clouds to get the elasticity you need to respond to changing research and clinical needs. Atom and BGA is a completely open source project, and I'll talk later about how you could be part of it. So the status quo in genomics. Every place I've worked has a big compute farm, and then it has a shared storage like Isilon or Parnassus, and that's the sort of HPC architecture, which is you often see in big research centers at least. And it works, but it has some inefficiencies, both in terms of developer time, in terms of cost, that are worth considering. Is there another option? So specifically, for a university or startup, the accessibility or cost associated with the HPC cluster in terms of capital outlay can be a major limiting factor, and you can't easily go to a vendor, a cloud computing vendor, and get an HPC architecture in the way you can get a large set of commodity machines from Amazon or Google. There's a sort of a goodness of fit problem between HPC and what you need to do genomics. That genomics is very I/O heavy, so it fits very well sort of the Hadoop ecosystem. Those bottlenecks. Again, the HPC storage solutions tend to generate these sort of location-specific bespoke models, which are then not very portable. And finally, the HPC approach, and here let me make clear the sort of pattern of cluster computing you use there would be sort of a queue. So like SunGrid Engine or LSF, you have a lot of jobs which are trivially parallelizable. You just put them into a job queue and they run on the farm. But that low-level API of job management requires that you manually split the data sets, which often is not done optimally. Chromosome 22 is a lot smaller than chromosome 1. Stragglers are a problem, so your entire there's not automatic restarting of a straggler if one of the nodes is slow or fails. So although you have a lot of compute power, the actual time it takes is limited by your very slowest job. And Hadoop and Spark in particular are all about minimizing that risk and bringing the entire compute, getting it finished in as fast as possible time. So this is why I started to get really excited, because I really enjoyed learning this over the last 2 years. Apache Spark is a completely different way to program in parallel computing and a cluster. It uses the cluster as a single computer. You program to that interface at the cluster level. You're not thinking about nodes. You're thinking about data abstractions like a collection, and you're computing on that. It just happens to run on the cluster. So Apache Spark's primary abstraction, the resilient distributed data set. It can be thought of as a generic collection API holding objects of arbitrary type, just like Java list. But that list happens to be distributed across many machines, and the framework itself knows how to distribute, compute, and parallelize on that collection. But as a programmer, I just think of it as a large collection, for the most part. There's a few details where you need to decide how to partition and apply some logic, but for the most part, you're programming at the level of the data structure, not the level of the physical cluster. So if you've worked with Java 8 at all, and sort of the functional aspects of it, like map and reduce and such, the core Spark execution API allows users to specify to a high level API a set of transformations and actions such as map, reduce, filter, group by, sort, join, sum, and count. Again, on that distributed collection that just happens to be across many clusters, or if you're testing or developing your code and you're on a single machine, it acts exactly the same. I'll talk about that sort of ease of scalability and development later. So to give you a picture of the flow of data, execution begins with a data source, often on the Hadoop file system, but it can be any source that basically all the machines in the cluster have access to. So it could be a network storage solution. It's just that you don't benefit from sort of the data locality as much as you would if you use HDFS. The file itself, I mean, we can natively read FastQ and BAM and VCF. There are nice libraries which are in the public domain, actually that we use for other sources, that read those files. So you don't even have to use our sort of improved implementations if you don't want to. You sort of read the native existing formats, but you gain speed and benefits if you write it back out to the optimized formats I'll talk about later, the Atom, Parquet, and HBase. But this emphasizes our complete compatibility with existing standards. The results of execution, if it's summary, if it's counting or generating p-values, if it's a small summary data set, you collect it back to the driver program that is sort of managing the application you wrote. Or if it's a large data set that you've transformed, you write it back to HDFS, and then you do further processing. So it's data in and data out in that way. This is more details about the internals of Spark. So Spark, or its API. Spark represents a series of operations as a set of graphs, which is lazily evaluated. So this took me a bit of time to get my head around. But as you're programming, you line up this long series of maps and filters and reduces and group bys. But it's not actually executing them. Even if you're working at the shell and you're typing that in, it's not executing them until you finally execute the final action. So it's building up implicitly this graph, but from your point of view, it's just applying the series of implicit operations. You don't have to think about the graph, but it's there. And this gives Spark execution framework the ability to be very smart. It's kind of like, I think of it as like being inside of a database optimizer, but you have just a little bit more control than you would if you were using, Oracle or something. Spark knows when a given step, like say a map or a filter, so the data is partitioned across machines. It's this big collection, and something like a map or a filter can be applied on each individual element without need of knowledge of elements in the other partitions. So those all get pipelined into a single run on those machines. It's called narrow dependency, and so you get a lot of efficiency in terms of data just moves through RAM on those machines. In fact, there's even some steps where it sort of recompiles in the newer versions of Spark. And then for steps where you do something like a group by, you would have to count and talk between nodes. It handles all that in the background. You don't have to think about it. So specifically, sorry. We need to go back to presentation mode. Is there like a on the far? All right, sorry. So specifically about the in-memory execution. In the traditional Hadoop ecosystem, after each sort of step, you write back to disk. And one of the big selling points of Spark is that it keeps intermediate steps in memory, which is especially valuable for the initial application they wrote Spark for, which is machine learning. And there's incredible 10x, 30x performance improvements over traditional Hadoop in Spark. But even if there wasn't, the Spark API is so much nicer than the Hadoop API that you would use it even if it was 5 times slower. But it does have huge benefits. Apache Spark this is the point I was getting to earlier. It's a write once, run anywhere, at any scale framework. So you write the code you execute on your local machine, on 1 core, on 8 cores, is exactly the same code that will work well, in most cases, on a 1,000 machine cluster. The abstraction just scales by the framework just scales it. This reiterates that same point. And finally, the last point is that Spark is an enabler. I mean, I think that I can use Spark to solve problems now fairly effectively, and I don't have a great knowledge of how to write, multi-threaded code or how to manage parallelism at the sort of supercomputer level. But your average application programmer using Spark, I think, becomes Superman or Superwoman. You have a lot of power that you place in the hands of application developers, and I think that's largely why Spark is so popular. And this is just a. I'm sorry if you all are experts on Spark. Maybe this wasn't useful, but this is just quick. We're getting towards the end of the Spark part, the generic Spark part. Spark works sort of in two parts. You have a leader node, which can be an application. It can be a REPL that yourself, that shell that you're working at. But you have one that's not doing, the leader's not doing the processing, but it's orchestrating the processing. It's building up that graph. It's not big data, but it's building up the execution plan. And then the individual worker nodes all run a Spark JVM executor, and they read data that's on disk, and they bring the data into RAM, and then they manipulate the data according to the execution graph that moves forward. So it's just the simple worker and leader structure of Spark. And yeah, I think we discussed all of these things. That it's scalable, it's elastic, it has automatic fault recovery, it's easy to deploy in the cloud as opposed to trying to invent your own HPC architecture in the cloud. It has memory optimizations I just mentioned. It has a beautiful, easy to use API. If you can use Java collections, then you can use Spark. Okay, so the good stuff now. How do you apply this highly effective cloud scale parallel processing tool to the domain of genomics? The first step is how could you best represent data formats that will work well in that environment. So this is the architecture. I think this is sort of the crown jewel of the project. The data formats alone are extremely valuable. If that's all you take away, you might want to use that in another project. If you think the rest of our application isn't worth considering, take a look at the fundamental schema and formats here. It was designed to mirror the effectiveness of how the internet works. So the internet is effective because the internet protocols built on TCP/IP, and then the levels above and below it work effectively because they have good, solid, clear levels of abstractions between each layer. So you can expect what to expect from TCP. HTTP knows what to expect. JavaScript knows how it interacts in the system. And you can substitute in different implementations. So you can have Ethernet, you can have fiber, TCP/IP can run over any of those, and you still use the same schema. So we have the same sort of well stratified abstraction layers in the BGG Atom ecosystem. So we have the schemas and models, which I'll talk about next. You have multiple options about how you want to represent the data on disk in terms of compression and the order it's laid down on disk based on the access pattern you want to use. And there's multiple ways you could actually work the physical storage. Again, it could be shared storage, it could be HDFS, it could be MapR, many options, but they all drop in replacements because of the well-defined abstraction layers in the stack. Similarly, the primitives, which I'll talk about, to do things like counting alleles, joining two data sets based on genomic region. Those are primitives that are useful for many different algorithms and many different applications, and they're there for us and others to build algorithms on top of. So some data formats, you all probably well aware. Sequencer gives you FASTQ files. You align the FASTQ files to reference genomes. You get BAM or SAM, and you do variant detection, genotype calling. You get VCF files. The anatomy of a VCF file, you have this big header section, which has a flexibly defined set of tags, which you can describe as what their cardinality is, what the data type is here, and then those tags are used in different columns of the data down here. So this was a very effective format that was developed in the 1000 Genomes project because it was human readable, because it was simple. But it has at least one sort of major flaw, and that's that it doesn't have a very formal specification. The specification is a big PDF document that is a set of prose, basically. And you can tell that that's a problem because there are C, Java, Python, Perl, and R implementations, which are all just slightly different. And that's the difference between 95% compatible and 100% is very meaningful. It produces a huge amount of effort. If if this format was defined rigorously in something like Avro or protocol buffers, you can generate code in any language which you know is provably correct. It's just a huge benefit. And yeah, I don't need to sell it any further, I don't think, to this audience. But we don't want to be non-compatible with those formats. We don't want to reinvent them. I mean, they're not ideal in some ways, but we just want a better implementation of these formats that is compatible. And we have done that. Go to GitHub. The BG project's BGG formats is the repo that has these schemas. And if nothing else, take a look at them and see if they meet your needs, because you'll automatically be compatible with any module in our system if you implement those formats. I mean, that's the beauty of the abstraction layers. And you can mix and match what parts of it you want to use. I think I just said all of these things. Oh, there was one, let's misread all fields. I guess that's kind of a Parquet thing I'll talk about in a second. But one of the values, if you have this kind of format, if you lay it down on disks in a column-oriented manner, then you can have a lot of advantages in terms of not having to read all the data. If there's a column you don't need to read for a certain kind of query, you just skip it. And this is why column stores are used in analytics. So the solution, I kind of foreshadowed. Avro is a schema-defined data interchange format for nested data structures containing fields, maps, and lists, so basically a JSON object. It enables validation, code generation of getters and setters in many languages. Avro is much like protocol buffers or Thrift. I think we could have chosen any of those three to do our project. We happened to choose Avro. And so think of it as a better JSON. I can't say enough about how valuable having a computationally machine-readable schema is to any information science. And then Parquet is one way you could choose to write Avro-defined data to disk. Parquet is a column store that is compatible with Avro-defined schemas. And again, it allows relevant data to be read through predicate pushdown and projection, which makes some queries much more efficient. And the compression is quite good. Compression is better than a BAM file by about 30%. So this gives you just some idea of what an Avro schema looks like. You define a record called a variant, and you define a set of fields. It looks very much like defining a table in a relational database, but I don't think we have any here, but yeah, here's an example. This is an embedded object. So this variant annotation object is defined elsewhere. So it's just this sort of nested collection of objects. This is just a picture about what column store formats do. You have this table of data, and instead of laying out field from row 1, field from row 2, you're writing out serially in memory a big chunk, which is all of field 1, so you can very efficiently read all of field 1 only if you want to. So now we're going to talk one level up a bit about the common primitives that you would use to access data in these formats. I would specifically highlight here the join operation, because if you use bed tools or some other tool to join your annotation data, your genes, your exons, your DNA's hypersensitive sites, these all are defined as regions of the genome, and you want to join them with the genotype or aligned read data that you have. So this is an example where we provide a set of primitives to do those types of joins in different ways, depending on the size of the relative size of the data sets, that then you can use to build your own algorithms. So instead of delivering a sort of finished product, we're delivering a set of APIs at many levels that you can use to develop your own toolkit. So let's see, again, different types of joins that you can do that we provide. This is an example of how you would use, if you're joining a very small table, like the set of genes in the genome with a very large table of genotypes, you'll want to use a broadcast join, because it just makes sense to do it that way. One other interesting point is that the data structure the arbitrary data structure that you're putting into your RDD can itself be a data structure. So if you want to store a interval tree as the objects that are distributed across your cluster, then you can do that. So essentially any type of complex algorithm you want, Spark can help you operate on it in a parallel manner, and it lets you write your own code to interpret and do what you want with each chunk. And that's essentially what the new APIs in Spark 2.0 are. It's an application built on top of Spark, which has some good columnar compression and these kinds of things. And so we're trying to decide right now if Spark 2.0 and some of those newer APIs is useful to use directly, or if bioinformatics is a specific enough domain that we really just need our own sort of data structures. We have flexibility to do that. whatever we choose, Spark is a good executional framework to manage parallel execution. How are we doing on time? How are you?
We're good.
It's been like 15 minutes? Or okay. Okay, so there's 3 ways you could use Atom. They're all useful for different purposes. You can use Atom at the interactive REPL. And when I first learned Python, and when I started with Scala and Spark as well, I always thought this REPL work seemed pretty hokey. I thought it was just like what you would do when you're teaching somebody. It's a good instructional tool, but it's not actually how I would work with data in any serious way. But actually, it's extraordinarily useful, and I'll talk about it in a second. So you can sort of get in there and play with things and code and be inside of the code to try things out. And it works well in Scala because as opposed to Java, writing Scala is much more like writing Python. You don't have to write all the types. It infers lots of things, so the code is very concise. It's concise enough that you can work it within a REPL, but you have all the benefits of sort of a strongly typed language. So you can work with the REPL. You can work with it as a library, as a programming API, and if nothing else, use the data format standards I talked about in Avro a minute ago. So if you're a developer, you want to build new tools, or you think our tools aren't good enough, at least use the low-level primitives and data formats and build onto it. And contribute your code to the project or create your own partner project. That would be great. And you can use the system as a user, as a completely naive user if you want. You can treat it as a command line interface, just like you would run a BWA or something else. You probably don't know all the internals. Just use it as a command line application. So speaking about how you would use this at the shell, so I don't show the prompt here, but this is what you would type in at the shell to do the action of loading some reads into well, it's actually a container, but it loads reads in, and this happens to be an already aligned file, but it takes the reads out of this file, it puts them into this container object, and then that container has an RDD actually in it, and then this shows you some of the examples of the type of transformations you do. On that RDD of reads, you do a flat map to pull out individual k-mers. Then you, this is basically word count. You pull out the k-mers and you reduce them by unique keys. You have a swap of the tuple there is, and then you sort by the key. And you end up with the number of here I guess the topmost 21 k-mers. If you want a good example of some of the motivation for using Spark at the REPL, and also there's a chapter that Uri wrote specifically for BGG Genomics. This is quite a good book. Okay, so using BGG as a set of libraries if you're a developer and you want to build onto it. Again, you can choose to use the API at various different levels. Applications which just use BGG formats are sort of automatically compatible. And you could write your own modules and you could plug into other modules where you like that we wrote. You can use the primitives as I described. If you want to write a variant caller or a genotype caller, then you'd start with the primitives we supply, and then you would add on the specific algorithm logic that you want to do from that. And then finally, the sort of downstream application level functions that do things like base quality score recalibration or marking duplicates. These exist as individual functions, which if you're writing a pipeline, you could choose to call them as functions as opposed to using the CLI. And we eat our own dog food. So the downstream applications that we've built, like Avocado, a variant caller, Mango, a visualization tool, Noki, a statistical genetics package, look for genotype-phenotype associations. These are all downstream applications which build on primitives that are supplied by the core Atom APIs, which obviously make use of the core Atom Spark framework. I guess the takeaway is that it's not a monolithic application where you don't know what's in there. It's a tiered application with lots of hooks where you can dive into it at whatever level you want to, and develop or use. This is just an example of the atom command line. So the atom submit is the start script for launch script. And if you don't know for anything, it gives you this help and lots of help and more help. Yeah. So this is an example of calling a command. There's a flagstat command that also exists in SAM tools, and Picard has a version as well that it takes a BAM file and produces some statistics about the number of reads, the number of duplicates, these kinds of things. And so you would run it using atom submit, the name of the command, flagstat, and then the data file itself. Flagstat is actually a good example of where using Parquet was very, very useful, because flagstat only really needs to read the column that has the byte flags, and so it's like several orders of magnitude faster to use Parquet as the source of data for running this kind of QC filter than to use the BAM file itself. This is just another example of how you go from a BAM file and convert it to this Parquet optimized columnar store data. There's no data loss between these two, and you can produce the BAM file back from here. That's a good point. So, like when we do this right now, as we're in the process of developing our own variant caller as well. Right now, for production sort of purposes, we still just basically plug into the GATK help type caller as our variant calling. So we do the initial steps. Here we run the QC, like flagstat mark duplicates in Atom because it's more scalable, much faster, and then we end up producing, if we change this to make this the Atom file and make this the BAM file, then it transforms it back into BAM, and then you can then use GTK in your subsequent steps. So you can use whatever parts of the pipeline you like, and it can go sort of back and forth between these existing formats and the sort of optimized Parquet here. If you run this, you'll find that this actually produces a directory. Inside that directory are the sets of Parquet chunks. And if you're on the cluster, those Parquet chunks will be distributed across to HDFS. Okay, but the beauty of Spark is you don't have to think about that. So just a word about Atom performance. It's always hard to benchmark and measure performance, but the end-to-end pipeline, largely because we're so much faster at mark duplicates and some of these other steps here, the end-to-end pipeline from FASTQ file to called genotypes is 3.5 times faster and 4 times cheaper than using the GATK best practices, and statistically equivalent in terms of the results. This graph shows some of the nice scalability of the cluster, and so you can take advantage of the elasticity and make it go as fast as you like. All of these functions, except for flagstat, because it sort of already is so fast, all show your linear scalability as you increase the number of cores. So it does what we want to in terms of horizontal scalability. And finally, you can save money. You can utilize spot instances, which can save 5 to 10 times the cost, and specifically because you can evenly distribute the amount of work across the cluster. You can do the amount of work you need to do in maybe an hour, maybe 2 hours, and so you have a much less exposure to the fluctuations in the spot market because you've run it so quickly. So you can use we use spot market instances ourselves. It also works because Spark is robust to failure, so you really can lose a few nodes or many nodes, and it will still complete the computation. And the point here is important. That if you're using this in your production pipeline, it's not like you need to pay for a large Spark cluster that exists permanently. All the persistent data you're going to keep on S3. Then when you want to do a computation, because it's free to move between S3 and EC2, you spin up a cluster that has HDFS and Spark running on it. You do a mass parallel copy from S3 to your sort of ephemeral cluster. You do the work you need to do, and then you write it to HDFS, and then you do a mass parallel copy back to S3. Okay, let's see here. So deployment, we have several recipes for how you can deploy on particularly Amazon. It's easy to do and automated. Tools. I talked already at length about integration with existing tools. and we want because you're using a substrate which isn't a custom hardware architecture, using something that can be run by anybody who has access to in the case of Amazon, the same hardware that environment that anyone else does. I'll talk in a second about how Docker really further makes your workflow work exactly the same in an in-house cluster, a single machine, or on in the cloud. So one of the technologies I'll highlight here comes from our collaborators at UCSC. It's part of their BD2K project. It has encapsulated, you can go to this Docker library here, but it has encapsulated all of the components of the Atom and BGG ecosystem, along with many components like BWA and GHE, haploid caller, all as Docker images, so that when we deploy these on the cloud, we have sort of complete reproducibility and containment, separation between what libraries happen to be installed on the machines and what runs. There's the Toil workflow engine which we use, which is it's a meta-level scheduler. So you have Spark, which is executing your parallelism within your Atom job. But if you're running haplotype caller as a downstream caller, or you're running BWA or bowtie as your aligner, you need a way to orchestrate the data in and out of those different steps. And so Toil is itself builds a graph of which the Spark execution can be a part. So you can link all of these pieces together. It works very nicely. At CG Cloud, you also would find the repository for that at the BD2K Genomics site. Is a AWS deployment script. It uses the Python Boto APIs to do all the work of deploying the instance you would need with Toil and Spark installed. So this is getting towards a turnkey solution very much. This is just some more details about Toil. It's been run at very large scale and works very well. This is just a picture of how you fit in third-party solutions like GTK, BWA. You have an Atom step here, and then within the Atom step, you spin up the Spark cluster, and we call that a service job within. Okay, and this is getting towards the end of the talk here, actually. Something I've worked on quite a bit over the last 6 months is expanding the number of options we have at the on-disk storage layer. So Parquet is an ideal format for scanning an entire sample or an entire data set. We have to touch all the data. It's a great primary archive for storage format because it has efficient compression. But when we started to build downstream applications like visualizations in particular, where you need to make ad hoc queries about small genomic regions, or if you had a particular set of clinical genes you were interested in and you wanted to quickly, I'm looking forward towards the time when we have 500,000 to 1 million samples, and you need to ask the question, for this particular gene, what is all the variation I've ever seen there? And that is not going to work if you have to touch, even just opening 1 million files will take a long, long time. So we need potentially another solution, and the cloud scale databases based on Bigtable, and the solution here we use is HBase, is definitely that solution in terms of a horizontally scalable database which can integrate new data and still keep a square table. And so again, this is an example where before this was Parquet, but because we have a well-defined interface here, we can substitute it in a different materialization layer, HBase instead of Parquet, and everything else in the stack still works exactly the way it did before. Something you would not get from monolithic applications, which was smashed at the stack. This isn't readable to you probably right now, but this just shows how we have this data warehouse layer. So this you can invert this. We have the data formats themselves. We have the archive and the large-scale batch processing. We have the data warehouse. You can longitudinally integrate new data sets by keeping them all together in one analytics database, which can be queried in sort of both axes. And then you have downstream applications, some of which maybe reach all the way through back here to Parquet, and some of which, like visualization, would reach into your sort of more real-time access database layer. So HBase, how many people are very familiar with HBase? Not too many, okay. So HBase is a sparse, distributed, persistent, multi-dimensional sorted map. And I thought this was very intimidating the first time that I started to learn about HBase, but it's really simple. I mean, if you like hash maps, and everybody likes hash maps, if you have one data structure, it should be a hash map. You have a row key, so we'll talk about it in a second. You have a column key, and together they get you to an individual cell. So you can think of HBase as just this gigantic table, but it has efficiencies because it is a hash map that any cells which are missing aren't costing you anything. And it's implemented as a data structure called a log structure merge tree, which manages the incremental writing of small sets of files as you update, and then in the background is merging them into larger serial archival files. So you always have trouble. You're trying to add the n+1 sample. You don't want to rewrite the entire database. People now, large genomic centers, are doing their data format for variants is one gigantic VCF file, and they have to continually rewrite the VCF file. And so this is the solution. This is for variant data. This is a dynamic VCF file that you can easily insert new data into at whatever scale. So looking at what HBase is, again, you have something defined as a row key. You have columns. You have whatever not random, but you have arbitrary binary data that you can interpret however you want to if you manage the serialization. And if you have missing data, it doesn't cost you anything. So let's look at and this is how it fits into Spark. You have HDFS, which is your you have your name node for HDFS. You have your master for HBase. You probably might be the same machine has your master for Spark. It doesn't really matter. But this is what's important is this is how the worker nodes look. Each worker node has a piece of the data. A piece of the data is stored in HDFS. And HBase is stored as files in HDFS, and then Spark Executor on the same machine is reaching into HBase and grabbing out specific regions, which become partitions, which Spark becomes aware of and then processes in the same way that it would process the partition if it had run it from Parquet. So this is how you might lay out the row key if you're using HBase. So the row key itself, the first element in your hash itself often is a embedded string which represents quite a bit of data. And so here, the underscores could be taken out. You could have a slightly more compact encoding, but you have a chromosome, a start position, a alternative allele, and a reference allele. That entire thing is the key for the first step in your hash. And then the next step in your the second dimension of your hash then could be sample name, basically. And the beauty of these data structures is it will scale as big as your cluster is, and with no troubles. And at least in the test we've done, the sort of retrieval rate for a specific region around a gene across arbitrary number of samples is quite good. So when to use HBase, if you need sub-second random access to region rates on a data store of 50 gigabytes to terabytes of data, hundreds of terabytes of data. If the data needs to be updated over time, as opposed to write once, Parquet is good for write once. When new data needs to be merged into indexed sorted order, so this might not have been clear, but in the HBase table, the rows are individual variants. They're like SNPs, and each new sample you receive is that sample for all the genotypes for that sample. You have to do a merge, so you can add that sample in, and yet the index itself is still sorted on variant position. And so that's what HBase is doing for you. It's doing this continuous merge process. HBase doesn't itself have secondary indexes, but there are lots of ways that you could do something like you put in the functional term like missense or nonsense or splice changing a variant, and then you could quickly pull out all of the potentially pathogenic variants by sort of creating your own secondary index, which could itself contain the data. Again, it wouldn't be that expensive necessarily to write the data completely twice, or you could just store the row key from the other table and look it up, sort of a 2-hop situation. So this code is still under development. It's not been merged into the main master yet, but you're welcome to take a look at the code in my repository, and I hope that within the next month or so we will see it merged in, because there's some challenges in terms of testing, because if you need to mock out some pieces of HBase so the test will actually run. You don't have to have a real HBase cluster to run against, but it does work. I think I'll kind of skip through these, but this just shows you some example. This is an example of why it's good to work in the shell. Like I did the development for HBase, all first prototyping it in the shell, and then gradually moving functions from the shell into actual classes. And to test or play with the data, you do this all in the shell. You say, I want this set of sample IDs. I want this set, this reference region. I want this chunk of region on chromosome 22 from 30 million to 31 million. And then you say, I want to load this RDD based on that query region and based on this set of samples. So it's taking a rectangular square, my massive data set. I want this set of samples down this axis. I want this set of variants on this axis. It's grabbing that square, which conveniently is going to exist on one machine and in nice sorted order, so it's not having to do a lot of work to get exactly the subset of data, the intersection that you wanted. Another point I realized as we were building the visualization stuff is that although Spark is very nice, and I think there is good applications for reading from HBase directly into Spark, there's also applications, I think, including building a genome browser perhaps, that there's really not a need. I mean, Spark is about orchestrating batch analyses. And so it may be, there's no reason why you need to use this architecture in a HBase to Spark situation. You can build it, and you can also access HBase directly, is what I'm saying. So upcoming work for HBase, we need to add functions in the command line interface so users can use HBase easily. We need to support, and maybe find some more clever ways to support GVCF. So a big issue, particularly in clinical genetics, is not what variants I found, but also what variants I could have found because I had enough coverage to see them. And so we need to represent that coverage data in useful manners. I'm kind of leaning towards not. I think the way that GVCF works is kind of a kludge. It's putting in these blocks of no variant information into the VCF file. I think there may be two different data structures. One represents coverage, one represents variance. Might be the solution. And again, you could just sign in RDD, which was that data structure, and then it would work very nicely with Spark. Another technology, also based on sort of the big table model of a distributed hash map, is Kudu. Kudu is specifically aimed at the middle ground between Parquet as a whole dataset scan technology and HBase as a real-time small query technology. Kudu tries to fit in the middle and serve both cases adequately, so you could avoid having to have two different data stores. It could be promising, so we're looking into Kudu. But the nice thing though is it still uses the row key in sort of the same way, and so I think that there'll be a lot of crossover. And I mentioned secondary indexing to speed up specific queries based on your use case. So that's at the end of HBase and very near the end of the talk. The next steps for the BGG project in general. We are working on staging more reference data sets, 1,000 genomes, all the encode data, and such into a format which is very easily used in BGG. So you can not have to, we can save the user certain steps of ETL there, and we call it the AGO project. We need to expand sort of the scope of the BGG solutions to bring our variant caller and as well our alignment solution into production, so that you can use BGG in production at all stages of the stack. Right now, some of the stages are still in development. We want to include the HBase model I just talked about in a future release. Spark originally was built to enable efficient machine learning. So there's all kinds of data science and machine learning which will become easier to do and more efficient once the data is in these formats, and it can take advantage of all the good work in existing machine learning primitives that are part of the main Spark ecosystem itself. We want to consider using more of Spark 2.0 and Spark SQL in the future, and we want to add more notebooks and recipes based on specific use cases, particularly to entice biologists and not big data people to see the value of this ecosystem. So this is the acknowledgement slide. Again, we have 52 contributors to the Atom BGG project from 12 institutions, and 25 contributors to the Toil and CGG Cloud project I just talked about. So it's really a cast of hundreds here at least. Yeah, UC Berkeley, Mount Sinai, what was Genome Bridge, Cloudera, Microsoft Research, and Santa Cruz are some of the biggest players. But we also have interesting sort of people coming out of the woodwork in Europe and other places that just put in a pull request every now and then. That's very nice. And finally, we welcome your contributions as users, as developers, and as partner projects. So don't feel like you need to put this name on your project to use the libraries and tools and formats that we want to bring to the community. We don't want to be the solution. We want to be part of the solution with you. So check us out on GitHub. There are 2 academic papers that are pretty extensive that you might want to read here, and I'm sure the slides will be available someplace. And then Databricks is a cloud platform built by the people that built Spark, and we have some demos running on the Databricks the platform that you might want to take a look at. That is it. I would love to answer questions.
Question.
Yeah.
At what point do you think that Atom will be ready for use in production environments? Sort of, I know that when I sort of evaluated when I was looking at it earlier anyway, it's still pre-version 1, right?
Yeah, it's still pre-version 1. I would have to go back to exactly when the 1.0 will come out. I would say the 3 to 6 month timeline, most likely. Do you have any opinion on that? Yeah. There are certainly components which you could use in production sooner. I think, like, for example, if you found the BGG formats and the Avro approach to things, you could take that or take it as an example and start to use specific components sooner. Please?
Yeah, I have 2 questions. One is, so would you use Parquet more for per sample data and then the HBase solution more for across multi-samples kind of analyses, or is this like kind of the separation you would do?
Yeah.
You mentioned that if you have like a lot of samples, eventually just opening the individual.
Yeah. So Parquet would definitely be good for individual sample analysis. That's for certain. But for any analysis which was going to touch all of the data, especially if it fits in RAM across the cluster, and across the cluster there's a lot of RAM. So it could be a good solution. If you need to get a lot of data from disk into RAM quickly, Parquet might be the solution.
And the other question would be like, if you have any thought on the GAP-K4 project, and how do you also like distinguish it?
Sure. So I think that the end goals are a little bit different. I mean, I'm convinced that they will be a big part of the future because of the success that they've had in the past, and because they're good developers. I see that product as more of an application and less of a development framework. I mean, maybe we're positioning ourselves where the room exists. I'm not sure, but I think that toolkit will be a turnkey application where we're trying to build something that developers and users can sort of join in at any level. And I think our fully open source commitment will help that happen.
Yeah.
Yeah, please.
Currently, it looks like you guys have exclusively focused on Spark. All your development that seems to be going into doing these new Spark libraries and things like that.
Mm-hmm.
But there's a lot of movement, even just in the data flow engine area, after the success of Hadoop. There's Spark, and there's a proliferation of other ones. In a few years' time, do you think it'll still just be Spark, or will there be plans to make it more? You can plug in other components, possibly from other engines.
I guess my hope would be that anytime you create good interfaces and good schemas, then it's going to enable that kind of diversification and interoperability. Yes, I think we support the idea of interoperability with other systems. I think for a batch execution system, Spark is pretty good. And I think that's probably the area we'll focus on in the near future, but we partner with other people. Yep.
Do you have some application or projects built on these Atom framework to share with us?
I'm sorry, I didn't quite
Do
hear
you
you.
have some example projects or applications built on this Atom framework to share with us?
Sure. So let's see.
Guacamole, which we presented here a couple meetups ago, uses some of the Atom components. Yeah, it's a semantic learning college that runs on Spark, and originally started out using a lot of the components in the Atom stack at all the levels, and I think it's moved to more just using some of the data formats now. But in my lab, we have also a longer tail of other sort of random genomic analysis tools that myself and others in the lab have written using a lot of the components. So the GitHub organization is Hammer Lab. If you just go there, you'll see a lot of repos that use some of this stuff.
Yeah. I mean, the Atom CLI itself, for example, for things like mark duplicates and base score quality realignment, indel realignment, I mean, that is a application level part which has been built there. I, as a toy project, built a eQTL analysis because when you're trying to compare all of the genotypes against all the all the transcripts, you have a lot of p-values, a lot of linear regressions to test, and that was a very good application of Spark. Other questions? Yep, please.
Would there be a change in speed, like when you for a variant analysis? Speed would it be faster?
I mean, to the extent that the operation was parallelizable, it will largely go as fast as you can add nodes to, right? So I mean, the collection will get split up so that there are equal parts on each machine, and they can all run in parallel. So if you have a relatively small, if you have 20 milliseconds to run on each machine, then your entire job could finish in near that time.
So I know you presented the HBase model. So the row keys, you mentioned that all the data in that query was localized to a single machine. So the row keys are the variant? It's a particular variant? So
yeah.
How did you make the row key?
So the row key is the variant.
Mm-hmm. And then what are you putting in each of the individual?
Oh, good point. So this is kind of a stand-in. So I think I showed the variant schema. Oh, wait, no, that was the variant. So something kind of like the where is it? Wow. So it's something like this. So there's variant, and there's another object called genotype. So we put the serialized object in there. So I actually did it two ways. It's to be sort of fully compatible with everything. You can just write the serialized object into that cell, and that works very nicely. It turns out there's also some tricks you can play because some of the data is encoded in the row key and in the sample ID. So you don't need to replicate that information. It's in the keys themselves. So you could make a small object that you can hold in the cell itself that takes advantage of information being encoded in the keys. I kind of think the optimization is premature, and just storing the serialized objects, which we nicely define in the cells, is a fine thing. I should also mention that there are other ways you could design the row key. There's a big literature about how to design these keys, and there's a problem with hotspotting in certain cases. Like if you,
are they sorted or?
They are sorted. So you would want to analyze your use case and your pattern and see if you want to add a salt value in front of this, so that you actually wouldn't store them in order, because then you could all the machines would run at the same time and put the data back, but then there'd be sort of a cost to reintegrating it. So I think this really boils down, this row key design, to experimentation with your data set.
And how many nodes in the HBase cluster in the example that you have?
Oh, so I mean the Berkeley cluster is 60 nodes with pretty beefy, like 24 CPUs on each, and it can retrieve any you load all of 1,000 genomes in it easily, and everything happens pretty instantly.
Any other questions?
I think one thing I would point out is the low startup cost to this. Is that I think one of the big appeals to the startup community should be, as opposed to investing in large infrastructure, you can run this kind of thing on the cloud and get started at whatever scale makes sense. We're trying to remove that barrier to entry, basically.
How many people are actively working on this right now?
Actively, I'd say there's 7 to 10 really active developers between the graduate students and then people like me and Michael and yourself. Yeah.
So students and then a few people who are like full time, like yours.
Yeah. So we have I'm full time. Another guy who works from Minnesota is full time. We have a couple graduate students who are very committed, and then a couple graduate students that work, as one of several projects. And then we have sort of the extended tail of people like Xavier and Neil, who have done major contributions. Actually, just kind of hop in sometimes, and there's a lot of traffic. We need to do a better job of sort of surveying our users, but we certainly see lots of interest from a lot of places on Gitter and such.
We'll help spread the word.
Yeah, please do. Use the formats if nothing else.
Cool. Any other questions?
Yeah, please.
Could you give one more overview of all the formats that are available? So you talked a little bit at the beginning about sort of a conversion from a BAM into an atom format. You said it was 30% smaller in that format. What does that format exactly look like? And you were saying later that you store raw data in Parquet. Are those, it's not the same raw data, it's different sort of formats that along the way you should store different things?
So, if I don't answer your question adequately, we'll talk later, but let me try. So we have Avro formats like this for a variant, for a genotype, for a read, for alignment, for a variant annotation, so for information like transcript information or consequences of the variant as another object. Some other structures that store like the reference genome itself and context from it. So we have a data structure for sort of all of the primitive objects you would use in genomics. And then, once they're specified like this, Parquet does all the work in terms of laying it down as the column store. And then when it's rehydrated and reserialized back into programming, it looks like this again as an object. Does that answer your question?
So all the work of deciding actually how to design the Parquet storage happens when Avro does that for you.
Yes, Avro, we don't do anything specific to tell. I mean, there's some optimizations. You can see how big the block size is in Parquet and this kind of stuff, but it has the same feel of code generation as it's just an automatic process.
So when you are doing that conversion, you're basically taking a BAM file and then converting it into a bunch of Parquet blocks, which, what is the .atom file? Is there a .atom file at all?
So the .atom file is a directory. Inside of it is Parquet blocks.
Oh, got it.
Yeah, it was a little confusing to me when I first looked at it.
Why don't any of the NIH genetics labs, why aren't they part of this consortium?
Good question.
Such specialized, not necessarily something like
I'm honestly less concerned about NIH than I am about Baylor and Broad, MIT, and Sanger, and the really large genome centers. I think that there's an organization called the Global Alliance for Genomics and Health, which we work with, that is trying to bring together sort of a internet scale collaboration to try to decide on these formats. But I think a lot of groups have a lot of investment in their local bespoke custom infrastructures, and so it's pretty hard to sell. It's also a different hardware profile. They have large farms of nodes with little disk and big shared storage, which actually can still run. This platform, you just don't get some of the benefits of data locality. I think there's some inertia in the field. I think that the value of taking advantage of all the work that's been done in big data will eventually overcome that inertia, and you'll see. There's no other project that exists, to my knowledge, that is in a position like this to take advantage of bridging the worlds of big data and business and analytics and using that technology applied to genomics. I mean, it's the right place at the right time. And we want to be completely inclusive of anybody that wants to ride that train.
Yeah, you said that VCFs, I mean, I found this from my experience as well, that VCFs are a format that are very difficult to actually read in a machine, that actually you need to put very specific logic in, depending on the VCF that you're reading.
Mm-hmm.
Is VCF parsing something that's built into Atom, or is that not something that's built in?
It's built in.
Yeah. So you can parse an arbitrary sort of VCF directly into these.
Yeah. Yes, and we've been doing a lot of work on that very recently, actually. I mean, the choice is always, we can take everything that's there if we just turn them into key value pairs. So when people invent, sadly, their own random additional tags and flags that they want to put into the file. So we do both. We try to see what are the most standard flags, and we make actual fields for them so they can be used in like projection and predicate pushdown and get all the benefits of Parquet. And then anything else that doesn't fit one of those models, we get shoved into a key value store. The one really challenging part of VCF is the split between multi-allelic sites. So you have these sites which have multiple alleles in some cases, and there's information that only makes sense in the context of that site being called. You have genotype likelihoods and such that only exist, that contain information about multiple alleles. And the model itself works much better if you split all alleles and teach them all as individual entities. So there's still some tension between exactly how to do that allele splitting.
Right, so you can't convert back into the same VCF in the same way as you can with that.
That is a problem for the multi-allelic sites, and we've been looking at the way that the GATK and other efforts do that, and they have exactly the same problem. That there's a certain mismatch there that is just hard to solve.
I have a meta question. I think it's a meta question about your. If I understand correctly, Avro is a format based on standard or spec.
At a meta level, yes. I mean, it's the rules about how to lay out fields is defined by Avro. Yeah.
You're saying that in the different BAM formats, it mattered very much which language you were in and how it got converted. It was in a very early.
Yeah. So the problem with parsing BAM right now is that the BAM standard is not very well defined, and you try to implement it in C or Perl or Python, you do it slightly differently. That's the problem. And if a unambiguous spec that you get when you do this, define it in Avro existed, then you could code generate correct access code.
Does that unambiguous spec exist, and how will that unambiguous spec have to be built out as new kinds of concerns and new kinds of information becomes available in data?
Yeah, this actually feeds into the other question very well, thanks. So yeah, we capture as much of this. I mean, we are defining what a variant is and which fields we can map from a VCF to this format when we define this here. I mean, that is making an attempt. And so if a new field becomes standard to use in VCF because of some new technology, it produces a new type of quality score or something, then for now it would either go into our random key value pair map, or we'd have to evolve the standard in time to treat that as a field. But one of the very nice things, especially about Avro, is that it has this ability to evolve a schema over time and still be backward compatible with previous versions. So I'm very, very optimistic about the choice there. Other questions? I think you had something else?
Yeah, I'm just curious about why you decided to sort of depart from the method that the VCF actually stores the multiple locations based on using the location as sort of key, and then you all have all of the alleles of the product model. Like, I guess it kind of does make sense to separate it, but in terms of data storage space, it would make sense.
Yeah, so I think that's exactly the row versus column mismatch that you deal with when making a choice between like Parquet versus HBase, like to decide what orientation to fix things. I think it comes down to your usage pattern. I think we try to provide the most granular format we can at individual cells at the schema level, but how that actually turns into storage on disk, say between HBase and Parquet, is where you would try to optimize that choice.
Okay.
Good.
Any questions? I think so. So please feel free to log pizza and beer, and yeah, maybe give a little more time debating who has any other questions.
Yeah, definitely.
Thanks everybody.
Thank you.